Okay, so hello and welcome everyone to week one of interactive live sessions for the course known as Fundamentals of Convective Heat Transfer. It's being offered by NPTEL and it's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering in IIT Guwahati. Uh, my name is Debjit. I'm currently a PhD scholar at IIT Madras in the Department of Applied Mechanics. And every week we shall be having these interactive live sessions. So, first of all, let me lay out the way we will do things here. So, the ideal scenario is to have as much interactions as possible because the lectures which you are viewing, those are unidirectional. They go from the side of the lecturer to you. You don't get to ask questions or, if you have some doubts to clarify them or, make any comment whatsoever just to make sure that you understood it well. So these sessions are here to bridge that gap. So in these sessions every week we will sit down together and go through some problems. I will present some problems at first. So the idea is to you should be ready to solve those problems. So for that we need to do a few things. First thing is to go through all the lectures of that week so that you have an idea about the content that we will be discussing. Then you should be ready with a pen and paper and possibly a calculator as well, because we might be doing some numerical problems from time to time. And most importantly, you should have questions which you should ask me, and have if you have any doubts regarding the material covered in the lectures, we can have a discussion on that, have an open discussion on that. uh, so this is how we will be doing things from now on. This is week one. So for 12 weeks of lectures, we will be having 12 such sessions, and then in the end we will have one summary session as well. uh, the main goal is to get acquainted with how to apply the knowledge that we learn from the lectures to solving problems, because that's what is required for completing your assignments, for appearing in the final exam as well. So that is the main goal over here. And learning and understanding, that tops the list. That's the main thing why we're doing any of this. So with that, let's get started. We will get started with some very easy questions. So we have question number one of today's session, which says select the correct definition of convection. Then we have three options, so read them carefully. Then once you have figured out the correct solution, you can either unmute and answer, or you can type in the chat box. And if you have any clarifications required, we can ask that, and have a intimate discussion about the entire thing. So this is the first question of today, which is asking us select the correct definition of convection. There are three options. Option A: heat transfer by the bulk movement of molecules within fluids. Option B: heat transfer by microscopic collisions of the particles and movement of free electrons within a body. And option C: heat transfer through electromagnetic radiation. So as the name of the course suggests, convective heat transfer, so there are multiple modes of heat transfer. uh, it's convective heat transfer that will be the primary focus of our entire course. So this first question basically lays the groundwork for that. What even is convection? Why are we, interested to study it? That forms, the later questions. First question is to, you know, first of all define what it even is. Okay, so we have a quick response by Palak Patel, who says that it's option A, heat transfer by bulk movement of molecules within fluids. Let's see if we get some more responses. I'd encourage everyone to participate in this. You can either type in the chat box or you can unmute and answer any way you feel comfortable. take your time, there's no hurry. So let's have a look at the solution now. So the correct answer is option A, heat transfer by the bulk movement of molecules within fluids. So heat transfer, as we know it, can occur through three primary modes, right? That is conduction, convection, and radiation. So radiation is the way in which heat is transferred through electromagnetic waves. So it's similar to the light waves or the radio waves as we know it. So it's all kinds of electromagnetic waves. They carry some energy along with it, and it's particularly the infrared rays which have a lot of heat associated with it. So any kind of heat transfer which takes place through this mode is known as radiation. That is option C over here defines what radiation is, and option B says heat transfer through collisions of the particles and movement of free electrons within a body. This is where none of the molecules actually move in a lattice structure. So let's say these are the molecules in a solid. So if the first one starts vibrating, this transfers that energy to its neighbor, then that in a similar fashion transfers that additional energy to its neighbor, and so forth. It carries on. So in this way heat is transferred from one direction to all the other directions. So the direction is also defined. It occurs from a higher temperature towards a lower temperature. And another mode in which conduction occurs is through the movement of free electrons. So let's say there is an electron associated with this particular molecule. So what happens is that in a solid, many such electrons are knocked out of this molecule or atom or whatever, and those electrons are free to move around within that solid. So in if some temperature gradient is set up, then these electrons also move from the direction of uh, higher temperature towards the direction of lower temperature, and they give off that energy and come back. So that's another mode in which conduction takes place. So option B defines conduction. It's option A that correctly defines convection, which is heat transfer by bulk movement of molecules within fluids. So convection can only occur within fluids because as we know that within a solid, molecules don't move around from one point to another. Their location remains fixed. But in a fluid, the molecules are free to move around. And make sure fluids doesn't only mean liquids. It can include both liquids as well as gases. So it's a common, misconception that fluids might mean only liquids. It's not so. Both gases and liquids are constitute fluids. Fluids basically means anything that can flow. So uh, what happens is if we have a solid boundary which is at a different temperature than the liquid surrounding it, then what happens is the molecules, the fluid molecules which are near to this solid boundary, they participate in heat transfer through conduction only. So at the interface, it's basically conduction only, nothing fancy about that. But what happens is after it, either gains some temperature or loses it, sorry, gains some heat energy or loses it, then it will flow, and some other molecule will come to take its place. So then again, it would gain some energy or lose some energy through conduction and again move away. So this conduction in combination with flow, that forms what we call as convection. So that is the heat transfer due to the bulk movement of molecules within fluids. I hope that's clear. Any questions so far? Any questions on any remarks that you would like to make? No. Okay. So it's a very simple one. We will move on. We will move on to the next question of today's session, which is asking us that del dot v equal to 0 can be written as the continuity equation under which circumstances or which conditions. For option A, steady incompressible flows. For option B, unsteady incompressible flows. Option C for both A and B. Or option D, none of the above. That is neither A nor B. So as we know that for convection, fluid flow becomes, one of the primary building blocks of learning convection. And fluid flow, as we know, is governed by the Navier-Stokes equations, which basically comprise of the continuity equation and momentum conservation equations. So this is the fundamental knowledge which we need to even move further towards understanding convective heat transfer. And one such important item over here is this continuity equation. And this question is related to that. So del dot V can be written as the continuity equation under which conditions. So as we know, continuity equation doesn't look like this. It's somewhat different. But for under certain circumstances, it can be simplified to this form. So the question is under which conditions would it be correct to write it in this form? Is it option A, steady incompressible flows? Option B, unsteady incompressible flows? Option C, both A and B? And option D, none of the above. So let's take a pause here. I think it's better to get to know each other. So, for this is a PG level course, not an UG one. So I'll hope that you must have had some, exposure to fundamentals of fluid mechanics or fundamentals of heat transfer a priori. So if you could, briefly introduce yourself and your background and maybe why you are even interested in learning this course, that would be awesome. I'll start by going first myself. I did my BTech in mechanical engineering, and then I joined as a, directly I joined as a PhD scholar at IIT Madras after that, and then now I'm working under Dr. Mahesh Panchagnula. He's, working on fluid mechanics. That's what he specializes in, and I'm working on that area as well. So fluid mechanics is basically a very, interesting thing for me. I spend my day learning it in, you know, different artifacts of fluid mechanics, not only related to my work, but I often deviate into other avenues as well. So if you could just, speak up and let us know uh, a little bit about yourself, that would be great. Unmuting and talking would be best. Otherwise, if there's a problem, you can type in the chat box. These sessions are supposed to be interactive, not one way. Like, then it doesn't serve its purpose. It'll just become like the weekly lectures that you've been watching. The main idea is to avoid these from becoming a lecture and more of a discussion. So, anybody who wants to speak up, feel free to do so. I hope I'm still there. I mean, am I audible or am I speaking to a screen over here? Hi, yeah. Would you like to, you know, tell us a bit about yourself? I mean, there's nothing to be, embarrassed about or ashamed of. Like, we're all here to learn. Anyway, seems like people are unwilling. I won't force it. So let's move on. So we have one response to this question in the chat box, which says it's option C, both A and B. Uh, any other responses to the question? The question is that del dot V can be written as the continuity equation under which conditions. So let me simplify this down a little bit. So del dot V equal to 0. This actually means del can be written as dodo x I cap plus dodo y j cap. Similarly, dodo z k cap as well. I'm keeping it down to, or let's write that down as well. Dodo z k cap dot v vector, which could be written as vx I cap plus vy j cap plus vz k cap equal to 0. Then if we do the dot product between these two vectors, then we will be left with dou vx dou x plus dou vy dou y dou vz dou z equal to 0. So writing this is the same as writing this. This is a more compact way. This is the expanded way of writing this. Sorry. So when can this be called the continuity equation? Is it when option A we are following steady incompressible flows, or when option B we are studying unsteady incompressible flows, or option C for both A and B, for both cases we can call it this way, or is it option D, none of the above? Okay, so let's have a look at the solution. The solution is option C, both A and B. So basically, if we write down the general form of the continuity equation, that is dou rho dou t plus dou dou x of rho u equal to 0, right? So we will consider the first case or both cases where if it's incompressible, regardless of being steady or unsteady. If it's incompressible, then we can write rho as some rho naught, which is a constant. In the more general case, this rho can be a function of space and time both. So x, y, z, and time. But when it's incompressible, this density rho becomes constant, equal to some value rho naught. This could be any numerical value, 100, 1000, 700, anything. So when it's constant, this time derivative goes to 0, and from this spatial derivative we can take this outside. So this becomes rho 0 into you know okay, I have not written this down completely. It's not just dodo x, it's dodo y of rho v plus dodo z of rho w equal to 0. Here I'm writing this vector v, velocity v can be written as u I cap plus v j cap plus w k cap. So this one can, so from all these three spatial derivatives we can take the rho out because now it's rho naught, and then this becomes dou u dou x plus dou v dou y plus dou w dou z, sorry, equal to 0. This rho naught can be taken out and the rest of this thing can be written as grad of v equal to 0. Oh, sorry, del dot v equal to 0. And this holds true for both these cases, for both steady and unsteady. And as a result, the correct answer would be option C, both A and B. Any questions on this? So this is a very useful assumption because it simplifies our continuity equation down quite a bit. But as we will see for forced convection where some heat transfer takes place, a little bit of fluid, it gains heat, its temperature increases, and as a result, its density goes down. So in that case, you can't have this assumption of an incompressible fluid, right? Any questions on this or any remarks you would like to make? I'm really eager to hear from you. I haven't heard a voice up until now. I'll repeat this again and again. No need to, hesitate or feel shy or feel embarrassed about saying something. Please don't do that here. We are here to interact and, have as much as a open discussion as possible. We learn a lot more when we, talk to each other about these things. Okay, so I'm hoping there are no questions regarding this one. So we will move on. We'll move on to question number 3 of today's session, which is asking us that Nusselt number can be thought of which of the following? Option A, dimensionless heat transfer coefficient. Option B, dimensionless temperature gradient. Option C, the ratio of convective heat transfer to conductive heat transfer. Or is it option D, all of the above? Take your time, there's no hurry. Try to figure out the correct solution to this. And once you have figured out, please unmute yourself and answer, or you can type in the chat box. So question number 3 of today's session is asking us Nusselt number can be thought of which of the following? Is it option A, dimensionless heat transfer coefficient? Option B, dimensionless temperature gradient? Option C, ratio of convective heat transfer to conductive transfer? Or option D, all of the above? Okay, so we have one response which says option C, the ratio of convective heat transfer to conductive transfer. Do we have any other responses? Would anyone like to contradict and give a different answer? Or you can agree and give the same answer as well. Do you agree that C is correct? Okay. We have both responses in favor of option C. So now let's have a look at the solution. The solution is actually option D, all of the above. Why? Let's go through each of them. So first of all, uh, option A says dimensionless heat transfer coefficient. So before dimensionless, what is heat transfer coefficient? Can anyone tell me? So in convective heat transfer, what is heat transfer coefficient? Does this equation look familiar? Over here, which term is the heat transfer coefficient? Is it Q, H, or A, or T, or T infinity? Which one? Don't hesitate to respond. Like you can give a wrong answer. It's not the end of the world. Which one is the heat transfer coefficient over here in this equation? Yes? No responses? Anyone? It's this H which is known as the convective heat transfer coefficient. So, yeah. So now this H is actually a dimensional parameter. We will discuss its dimensions later on. So this can be non-dimensionalized in this form. This becomes a dimensionless parameter, and as it so happens, this is exactly how Nusselt number is defined. So Nusselt number can be thought of as the dimensional heat transfer coefficient. Now let's have a look at dimensionless temperature gradient. So how do we write temperature gradient? In this fashion, right? Dou T dou Y or dou T dou X, whatever spatial gradient, whichever we are looking at. So now, this is a dimensional parameter. Now, in order to go to dimensionless parameter, we need to uh, non-dimensionalize both this t and y. So let's say we define a non-dimensional temperature t as something like t by t infinity divided by some tw minus t infinity. Both are reference temperatures which are relevant to the problem. And this y star, this can be non-dimensionalized as, let's say, uh, y divided by L, L being the relevant length scale associated with the problem. So now if we try to write down a non-dimensional version of this, so then T would become, let's say, then T would become, T could be written as in this way. So give me a second. So yeah, so in heat transfer, we can write K, uh, some Q equal to Ka into let's say dou t dou y. In this case, if we non-dimensionalize this, or no need of this, we will do it directly. So instead of dou t, this would become, dou t star divided by or multiplied by tw minus t infinity, and in the denominator, instead of dy, if we write dy star, this becomes L into dy star. We need to have an equation here. So let's start off with this equation in hand. We have q equal to ha into t minus t infinity. Now I'm trying to plug in these values. So q into ha, so this would be equal to some k a dou t dou y. Heat transfer coefficient dimensionless quantity तो नहीं है, हाँ. So heat transfer coefficient itself dimensionless quantity नहीं है, but if we try to make it uh, dimensionless, then it would be similar to the Nusselt number mathematically. Does that answer your question? Okay. Okay. So now if I write it down this way, so instead of dou t dou y, I'm writing it down this way, divided by L into dou t star dou y star. So as you can see, these two things cancel out, area cancels out, and finally we can write this dou t star dou y star should be equal to h into L by k, which is again the Nusselt number. So the dimensionless temperature gradient, this is also mathematically equal to the Nusselt number. So this is also a way in which it can be, a Nusselt number can be thought of as the dimensionless temperature gradient as well. And last but not the least, as the ratio of heat transfer to convective heat transfer to conductive heat transfer. So let's say I write down each of them. So Q conv, this is convective heat transfer divided by the Q cond, which is conductive heat transfer. Okay, I hope it makes sense. So this is the ratio that we are talking about. Ratio of convective heat transfer to conductive transfer. So how do we define, what is the formula for convective heat transfer? Can anyone help me with it? इसका फॉर्मूला क्या होगा कॉन्वेक्टिव हीट ट्रांसफर का? It's there written in this slide only. We have the formula written here, right? It's just h into a into t minus t infinity. And for conductive heat transfer, it's k a then dou t dou y, which we can write as t minus t infinity by L, right? So dou t dou x, that can be written as delta t by delta x. Here delta t is t minus t infinity and delta x is L, whichever length scale is associated with the problem. So now we can divide A from both sides, this delta T from both sides, and it ultimately becomes HL by K, which is again the Nusselt number. Sorry, which is again the Nusselt number. So option C is correct as well. So these are the three ways in which Nusselt number can be thought of. As a result, option D would be the correct answer, all of the above. Any confusion regarding this one? Is it clear? Okay, I've received a thumbs up emoji as it seems. Thank you for that. Okay, so if there are no doubts regarding this one, we will keep on moving. So we will roll down to question number 4 of today's session, which is asking us select the topics in which convective heat transfer might be of relevance. Is it option A, electronics cooling, option B, refrigeration and air conditioning, option C, industrial power generation, and option D, all of the above? So this question actually makes us think, why are we even trying to learn this? Where is it of relevance? Is it in option A, electronics cooling, option B, refrigeration and air conditioning, option C, industrial power generation, or is it option D, all of the above? So, question 4 of week 1. Select the topics in which convective heat transfer is of relevance. Option A, electronics cooling. Option B, refrigeration and air conditioning. Option C, industrial power generation. Or is it D, all of the above? Read the question carefully, try to figure out the solution, and once you have figured it out, you can type in the chat box or you can unmute and answer as well. Give me a second over here. Sorry. Okay, we have one response in favor of option D. Let's see if we get any more responses. So we have to select the topics in which convective heat transfer plays a role. Is it option A, electronics cooling, option B, refrigeration and air conditioning, Option C, industrial power generation, or option D, all of the above. So let's have a look at the solution. Solution is in favor of option D, all of the above. That means each of this electronics cooling. So, you know, uh, most probably, or you know, almost certainly, you are joining this session using either a mobile device or a computer. So irrespective of whichever device you're using, there will be a processor there. And as we know that with time, these processors are getting smaller and smaller. And within that small size, more and more number of transistors are being embedded. So our devices are getting more compact. So if we can remember, old computers, they used to be huge. Now we have, within the palm of our hand, or some specialized electronics are even smaller. Anyway, so the main thing is these uh, processors, as they are called, these are getting smaller in size and more transistors are being embedded within them. And more transistors mean more electricity flows through it, and as a result, more heat is produced in it due to the simple effect of Joule's heating. So, in order to, and we know that at higher temperatures, the electronics start to, uh, degrade in their efficiency, as well as other functional uh, properties are also lost. So, in order to make sure that our electronic gadgets keep working fine, we need to make sure that these are, sufficiently cooled. They do not, become very hot. So the heat energy has to be dissipated from it in some way. Then this concepts of convective heat transfer comes into play. Uh, Either we have a fan attached near the processor which blows air on it, and that is called forced convection, which cools these chips, so to say, or we can have heat pipes which take that heat away and dumps it somewhere else, and in that way cool the processor. So electronics cooling is a very relevant, active area where convective heat transfer is of high relevance. Many engineers are recruited in that process and they make a living out of it, all because of their knowledge of convective heat transfer. Then comes refrigeration and air conditioning. So for general comfort, both of these are required. And as of now, there are many applications where these are absolutely vital. So, in absence of, let's say, large scale refrigeration, so let's say in cold storages where we know vegetables like potatoes, which are produced in India, are stored in cold storages, right? So, they are basically, that's a very high scale refrigerator, nothing else. And these cold storages are very relevant to our Indian economy because it keeps the prices of those vegetables stable and ensures that there's a sufficient supply even when the production is low, or export from uh, other countries become difficult. uh, in all those situations, it forms really the backbone of Indian economy in that way. As we know, we are a heavily agriculture dependent country, and preserving our produce is absolutely vital. So, refrigeration in that way is a very crucial sort of engineering application of whatever we are learning. And air conditioning, not only for comfort, for well-being of many people, becomes very crucial. So in hospitals, ICUs, there you can't have uh, proper patient care without proper air conditioning. And as we know, we are probably suffering from a very bad summer this year. So whoever can afford air conditioning are going ahead with buying one for their home. So that's another vital area which will become even more important in the coming years, where convective heat transfer and its applications play a huge role. Then finally, industrial power generation. So we are basically nothing without electrical power. Let's face it. So industrial power generation, at each and every step of power generation, convective heat transfer plays a role. So may it be, the process of burning the fuel in order to release that chemical energy into heat energy, then it sort of, heats up some water, which is again heated by convective heat transfer, and that water flows from, you know from the combustion chamber to some, after it becomes steam. When water becomes steam after gaining that heat energy due to combustion, that steam then goes ahead and rotates a turbine, where again convective heat transfer plays a role. And then after it has crossed the turbine, there are cooling towers like this, you must have seen. In cooling towers, this steam is again condensed into water, and then this water is again fed over here. So this is the complete cycle of power generation. Power generation takes place over here from the turbine. This is where electrical power is generated. So in each and every step of it, be it in the combustion chamber, be it in the heat transfer from the combustion hot products to the water, and this water eventually becoming steam, that steam passing through the turbine, then that steam being cooled back to water. In all these steps, you can see convective heat transfer plays a very crucial role, and without the knowledge of it, efficient systems cannot be designed, right? Or existing design can't be improved. So for all this, a very strong knowledge of convective heat transfer is required. So as far as this question is concerned, all of the above would be the correct answer. Okay, anything anyone would like to add on top of this? Please feel free to go ahead. Is everything clear? Do you have any questions or any remarks to make? Is there any other topic where convective heat transfer might be of relevance that you can think of? Apart from these three, what other topics are there where convective heat transfer is important? Hmm? No answers? Any other topic where convective heat transfer might be relevant? For automobiles, it could be bikes, it could be cars. Anything else in the aerospace industry? It's very important. Then simple biological applications, when in biological systems, so let's say we are biological systems, right? Any living being is. So we have our own heat regulation system. So when we feel hot, we start producing sweat, which gets evaporated by the air surrounding us, and as a result that latent heat is absorbed by the sweat from our bodies, and that and after it gets evaporated, it gets it flows away. So that's where convection comes into the picture. So that's another area where convective heat transfer is of very high relevance. Okay, so let's not spend any more time here. We will move on to question number 5 of today's session, which is asking us to match the following. So on the left column we have conductivity K, and on the right column we have convective heat transfer coefficient H, and on the right hand side we have four options of different units. So you have to match the quantity, physical quantity on the left hand side to its unit. So these are the units and these are the physical quantities. There are more options on the right hand side than the left. So basically there are two incorrect options also here. So leave those out. Your goal is to figure out which one is which. There are four options given below. So these are option A, A1, B4, option B, A4, B1, option C, A3, B2, and option D, A2, B3. So which one would it be? Take your time, try to figure out the correct units of both these physical quantities. So we have a response option D, A2, B3, which means A2 and B3. So let's have a look at the solution. The solution indeed is D. Very good. A2B3. So how we can figure out is in this way. So let's say let's use the formula of conductive heat transfer over here. Ka dot E dot X. Right. For now, let's say we have to figure out the units of K. So I can write this K as Q by A into 1 over dot E dot X. So now let's write down the units of each of them. So Q is power, that is watt. Sorry, Q is in watts. Then we have area, which is in meters squared. Then we have 1 over dot E dot X. Now dot E is temperature, that is in Kelvin, and dx is meters length. So this one would cancel out, and finally we will get watt per meter Kelvin. So this is the units of K. So A2 was the correct answer to this. Then the other one, B, convective heat transfer coefficient H. So here again we will start in this way, Q equal to HA into delta T. So H would be Q by A delta T. Now let's write down the units of it. So Q is again power, watt, area is meter squared, and delta T is Kelvin. So very simply watt per meter square Kelvin, which is option 3. So B3 again is the correct solution. So A2 B3 option D is the correct one. So you did pick correctly. Very good. Any clarifications regarding this one? Is everything clear? How to do these kind of problems? So in the assignment or in the final exam that you'll face, you might get some other parameter, and then the question would be asked that what are the correct units of this parameter. So in this fashion, if you remember any one formula or any relation of which includes that parameter and the other quantities are known, then you can use that formula to finally arrive at the correct units of it. Okay. Cool. So moving on, we'll move on to question number 6 of today's session. This is a numerical type question. So consider the figure shown below. We have a wall over here, which has a thickness of L and an area of A, and there is a temperature difference across that wall. It's T1 in one side and T2 in the other. So I'll read out the question. Consider the figure shown below. Given there is a heat flux of 80 watt per meter square flowing through the slab and T2 is 300 Kelvin, dimensions of the slab are as follows: L equal to 0.5 meter and area A equal to 1 meter squared. Given that the thermal conductivity of the wall material is K equal to zero point 0.8 watts per meter Kelvin, you have to find what T1 is. Is it option A 305, option B 400, option C 350, or option D 320? Very much of a competitive exam type of question, which you should be able to solve quickly. But here there is no need of hurry. Please take your time and try to do this correctly and figure out what the correct solution of this would be. So this is what the simplified problem is. So I have something like this. There's a temperature T1 over here and a lower temperature T2 here. As a result, there is a heat flux through this Q. This Q I know. This is given as watt, 80 watt per meter squared. Now given that this thickness is L and the area of this slab is A, what would be, and T2 is also given. T2 is 300 Kelvin. So T1 equal to what? This is the question. And mind you, heat flux is given, not just amount of heat per unit second or power. It's the flux is given 80 watt per meter squared. So this is basically Q by A. The conductivity of the material is also given. It's zero point 0.8 watt per meter Kelvin. So what would be the value of T1 in this scenario? Everything else is given. You just have to find out T1. Simply use the formula of conductive heat transfer and plug in all the known values. You should be able to get the correct answer. Once you figure out the solution, please unmute and answer, or you can type in the chat box. If you need any help, please let me know. I'm here to help. But try to solve it yourself. Okay, so let's have a look at the solution. It's option C, 350. So we will simply write down the equation of conductive heat transfer. So Q equal to Ka into T1 minus T2 divided by L. Now heat flux is given over here. So 250, ठीक है 250 नहीं आना चाहिए कोई एनीवे लेट्स आई मैं सॉल्यूशन कर रहा हूँ यहाँ पे आप देखिए अगर किसी स्टेप में मिस्टेक हुआ हो तो the flux q dashed as I call it, so it would be q by a, and from this formula it would be something like k into t1 minus t2 divided by L. Now this value of this flux is given as 80, and now k would be zero point 0.8, L is zero point 0.5, and here it's T1 minus T2. T2 is 300, right? So let's solve the rest of it. So if I divide 80 by zero point 0.8, it should be 100, and if I multiply it with zero point 0.5, then T1 minus 300 would become 50, and T1 would become 300 plus 50 equal to 350 Kelvin. So this is how we can arrive at our answer of 350. Any problems?
T2 माइनस T1 भी तो कर सकते हैं
हाँ T2
सर T2 माइनस T1 क्यों नहीं किया
हाँ क्योंकि यहाँ पे एक तो मतलब क्या बोलते हैं विजुअली ये दिया हुआ है कि T1 शुड बी ग्रेटर देन T2. सिमिलरली आप अगर T2 माइनस T1 करेंगे यहाँ पे तो सॉरी सिमिलरली यहाँ पे अगर T1 माइनस T2 के जगह मान लीजिए अगर आप T2 माइनस T1 करेंगे तो फिर दैट वुड रिजल्ट टू T1 बीइंग 250. So you are correct in that way. Something that should have been mentioned is in the question is that T1 is greater than T2, or the Q is flowing from T2 to T1 from T1 towards T2. That directionality was not clear. I suppose that's why it caused that confusion, right?
ओके सर
Okay. Either way, you are correct in that way. 250 be correct hota. Okay, so we will move on to question number 7, which is asking us select the law that determines the radiative heat flux for a body. Is it option A, Stefan Boltzmann law? Is it option B, Planck's law? Is it option C, Kirchhoff's law? Or is it option D, Wien's displacement law? Radiative heat transfer, QRAD. कौन सा फॉर्मूला है जो रेडिएटिव हीट फ्लक्स को डिटरमाइन करता है? Is it option A Stephen Boltzmann law? Is it option B Planck's law? Option C Kirchhoff's law? Or is it option D Wien's displacement law? Option A Stephen Boltzmann law. We will look at the solution and it's absolutely correct. So how do we write Stephen Boltzmann law? क्या है फॉर्मूला? कोई एक सॉलिड बॉडी है जिसका एमिसिविटी है एप्सिलॉन और टेम्परेचर मान लीजिए है T, तो फिर रेडिएटिव हीट फ्लक्स कितना होगा? इसका फॉर्मूला क्या होगा अकॉर्डिंग टू स्टीफन बोल्ट्जमैन लॉ?
Five into -8
सॉरी, आपका वॉइस थोड़ा सा ब्रेक हो गया, फिर से बोलिए।
equal to sigma e t to the four.
हाँ, सिग्मा एप्सिलॉन टी टू द पावर 4। ये ई नहीं एप्सिलॉन है। एनीवे, दिस इज एमिसिविटी। तो
A
हाँ सॉरी, यहाँ पे ए भी होगा।
sigma epsilon A into A sir.
अभी अभी ठीक है या फिर गलत है कुछ? ये फॉर्मूला ठीक है ना? ओके, सो दिस इज स्टीफन बोल्ट्जमैन लॉ। ये सिग्मा का वैल्यू 5.67 into 10 to the power -8,
-8.
right? याद रखना इजी है, 5 6 7 8।
Yes sir.
ठीक है।
Yes. Yes sir.
This emissivity would depend on the surface property of the body. For black body it would be perfectly 1. For other kinds of bodies it would be somewhere between 0 and 1. Okay, good. So we will move along to question number 8 of today's session, which shows us two figures, and it's asking us, among the two figures shown below, identify whether they depict an external flow or internal flow. And there are two options, which are basically the two alternatives which could be possible. Figure 1 showing internal flow, figure 2 showing external flow would be option A, and option B would be figure 1 external flow and figure 2 internal flow.
सर क्वेश्चन ही नहीं समझ आ रहा है।
हाँ,
सर क्वेश्चन नहीं समझ आ रहा है कि इसमें इंटरनल फ्लो, सर बॉडी कौन सी है इसमें?
यहाँ पे ये है बॉडी, ये जो स्फीयर है और उसके ऊपर से फ्लो हो रहा है, और यहाँ पे
तो सर
दो वॉल्स है, इस तरफ एक वॉल है, इधर एक वॉल है, और उसके बीच में से फ्लो हो रहा है। तो कौन सा एक्सटर्नल फ्लो होगा और कौन सा इंटरनल फ्लो होगा?
फिगर 1 में इंटरनल फ्लो हो जाएगा, फिगर 2 में एक्सटर्नल फ्लो।
Okay, so option A is your response. Let's look at the solution. The solution is actually opposite. So figure 1 is showing an external flow because मान लीजिए यहाँ पे एक sphere है और इसके ऊपर से flow हो रहा है, कोई confinement नहीं है। The definition of an external flow is that it's an infinitely large the uh, flow flow outside the body that can go till infinity. मतलब यहाँ पे जो फ्लो है आई कैन कीप गोइंग टू इन्फिनिटी, कोई मुझे रोकने वाला नहीं है. So it's as if
Yes.
there's an infinite ocean, and within that there is this sphere which is like a ball within an infinite ocean, और उसके about flow हो रहा है. तो इसलिए this is external flow. और ये जो सेकंड केस है फिगर 2, इसमें ऑलरेडी दो वाल्स है जो कि इस फ्लो को कन्फाइन कर रहा है. सिर्फ जो भी फ्लो होगा इन दोनों के बीच में होगा, बाहर कुछ नहीं होगा. तो दैट्स व्हाई
Okay.
दिस इज एन इंटरनल फ्लो. ये डिफरेंशिएट करना यूजफुल क्यों है, क्योंकि हम लोग बाद में जब कॉन्वेक्टिव हीट ट्रांसफर के और डिटेल्ड केसेस सीखेंगे तो वहाँ पे ट्रीटमेंट अलग होगा. मतलब एक्सटर्नल फ्लोज के लिए उसका मैथमेटिक्स अलग है और इंटरनल फ्लोज के लिए उसका मैथमेटिक्स अलग होगा. ओके.
Yes, sir.
ओके. So very quickly we will keep on moving. So we'll move on to question number 9, which is asking us, which is again a match the following type of question, where these are, types of boundary conditions and their mathematical expressions. So ये जो लेफ्ट वाला कॉलम है इसमें डिफरेंट टाइप्स ऑफ बाउंड्री कंडीशंस है. डिरिचले बाउंड्री कंडीशन, नॉयमन बाउंड्री कंडीशन, रॉबिन बाउंड्री कंडीशन, एंड ऑप्शन 4 कॉशी बाउंड्री कंडीशन. और कुछ मैथमेटिकल एग्जांपल्स है राइट हैंड कॉलम में जो कि कोरेस्पॉन्ड करते हैं एक कोई टाइप ऑफ बाउंड्री कंडीशन से. So the goal here is to match them. So we have option A, dou y dou x equal to some f. Option B है y equal to f. Option C, c1y plus c2 dou y dou x equal to f. And option D, y equal to f1 and dou y dou x equal to f2. तो इनको मैच करके कुछ ऑप्शंस मिलेंगे which should be among option A 1A 2B 3C 4D, or 1B 2A 3C 4D, or 1A 2B 3D and 4C, or it could be 1B 2A 3D and 4C. Which would it be? Once you match a few, you should get an idea and you don't have to solve all four of them. If you have any questions, you can ask.
नो सर, 4 ऑप्शन पैची फॉर्मूला तो पढ़ा था बट याद नहीं, बाकी के पढ़े भी नहीं है.
ठीक है, कोई बात नहीं. We will.
न्यूमेन
हाँ.
न्यूमेन भी पढ़ा है बट फर्स्ट और थर्ड नहीं पढ़ा है अभी तक.
फर्स्ट और थर्ड नहीं हुआ, अच्छा ठीक है, कोई बात नहीं. We will look directly go to the solution. So solution is 1B 2A 3C 4D. So let's figure out each of them. Dirichlet condition. Sorry, Dirichlet. So Dirichlet condition में क्या होता है, कोई भी एक बाउंड्री हो उसमें जो भी वैल्यू होगा वो हम बोल देंगे, मतलब डिफाइन कर देंगे कि इसका वैल्यू इतना होगा, 5 होगा, 10 होगा, 11 होगा, कुछ भी. तो y इक्वल टू एफ, इस तरह का अगर बाउंड्री कंडीशन हो तो वी कॉल इट अ डिरिचले बाउंड्री कंडीशन. तो 1 मैच होगा b के साथ. फिर आता है 2, जिसमें है नॉयमन बाउंड्री कंडीशन. ये आपको ऑलरेडी पता है. तो इसमें क्या होता है कि हम कोई ग्रेडियंट बोल देते हैं कि डो वाई डो एक्स, या फिर सम डो टी डो वाई. इस ग्रेडियंट का वैल्यू हमको मालूम है, एक्चुअल वैल्यू कितना है वो नहीं मालूम. मतलब एक्चुअल वैल्यू लेट्स से 5 हो सकता है, 10 हो सकता है, कुछ भी. लेकिन डो वाई डो एक्स इसका एक फिक्स्ड वैल्यू होगा कि 7. तो it could be like this. So let's say x goes from 0 to 1 over here, and at x equal to 0 I'm telling that the dou y dou x would be equal to 7. So if y is 5 over here at x equal to 0, so at x equal to 1 it would be 5 plus 7, some 13 होगा. सॉरी 12 होगा. अगर 5 के जगह यहाँ पे 6 है तो ये ग्रेडियंट सेम होगा. at x equal to 1, the value would be 13. Anyway, it doesn't matter. In Neumann boundary condition, what is done is the gradient is specified. Sorry, not the value itself, but some gradient of the value that is specified. That is a Neumann boundary condition. फिर आता है ऑप्शन सी और ये मैच करेगा ऑप्शन ए के साथ, तो 1b 2a मिल गया. अभी 3 रॉबिन बाउंड्री कंडीशन जो है, रॉबिन बाउंड्री कंडीशन इज ऑल्सो नोन एज मिक्स्ड बाउंड्री कंडीशन. इसमें क्या होता है कि वैल्यू और ग्रेडियंट दोनों का एक कॉम्बिनेशन होता है, मिक्स कर देते हैं उसको. सो उसका कोई भी लीनियर कॉम्बिनेशन, जैसे c1y प्लस c2 डो वाई डो एक्स, इसका वैल्यू हम लोग मेंशन कर देंगे. तो ये मैच हो रहा है सी के साथ. तो दिस इज नोन एज रॉबिन बाउंड्री कंडीशन. ये कॉन्वेक्टिव हीट ट्रांसफर में काफी इंपॉर्टेंट है, हम लोग देखेंगे बाद में. फिर आता है लास्ट वन, कॉशी बाउंड्री कंडीशन, जिसमें कॉशी बाउंड्री कंडीशन एक्चुअली में डिरिचले और नॉयमन दोनों का एडिशन है, बोल सकते हैं कि दोनों फिक्स्ड होगा. y इक्वल टू एफ भी मेंशन कर देंगे हम, और डो वाई डो एक्स इक्वल टू सम, इसको f1 बोलते हैं और इसको सम f2 बोलते हैं. तो we will define both the value as well as the gradient over here. So finally we get 1b, 2a, 3c, 4d. So option B would be the correct answer. Any questions on this one? We discovered some new types of boundary conditions over here. So, any questions?
No, sir.
Okay, cool. So now we are nearing the end of today's session. This is the last question from my end. So we have to select the correct statements now. We have three statements over here, 1, 2, and 3. Statement 1 is free convection is caused due to buoyancy differences, buoyancy forces, and density differences. Option 2 is forced convection is driven by some external source. Statement 3 is in general, the heat transfer coefficient for free convection is higher than forced convection. तो इन तीनों में से कौन से ऑप्शंस करेक्ट है, that we have to select. And the options are option A 1 and 2 only, option B is 2 and 3 only, option C is 1 and 3 only, and option D is all of the above, that is all of them, 1, 2 and 3 are correct. So read the statement carefully and try to figure out which one is correct and which one is not. Option D, all of the above. So you're saying that all of these statements are correct. Let's have a look at the solution. The solution is option A, 1 and 2 only. Why? So let's figure out why option 3 is incorrect. But first, let's go through the initial two statements. So the first statement says free convection is caused due to buoyancy forces and density differences. That is true. So in forced convection, what happens is that we have a hot wall like this. So what happens is the particles near this, they get heated up, and as a result they become lighter and they flow up, and the fluid sitting at the top, that flows down as it's heavier than this hotter fluid, and this again gets heated up and this again moves up, and this way one convection current is set up in a circular fashion, which takes away heat from this hot wall. So that is called free convection, and that is primarily driven by the density differences and buoyancy forces. Statement 2, so this is correct. So statement 2 says forced convection is driven by some external source, like there would be a pump or something that is driving a flow, and as a result causing heat transfer by convection. So that is known as forced convection. So if you have a fan rotating on top of your head, that is blowing some air onto you, and that fan is the external source which is driving the air towards you, and causing forced convection over your skin, so to say. So forced convection is driven by some external source. And as far as our example is considered, the fan is the external source here. Option 2 is also correct. Now option 3 in general says that heat transfer coefficient for free convection is higher than forced convection. This is wrong. Forced convection is generally uh, that has a higher heat transfer coefficient as compared to free convection. Otherwise, I'll go back to my example of a fan. So let's say it's a hot day and you are sitting in quiet air in your room, and you have not turned the fan on. So then also you're losing heat to the air around you, which is again getting lighter and setting up these convection currents around you, and that is free convection. As compared to that, when you turn the fan on and air is being blown uh, over yourself, then you'll feel that that convection, that rate of heat transfer would be much higher than what it was when the fan was off. So that's a very simple example demonstrating the difference between forced convection and free convection. And from our common experience, we can say that forced convection has a much higher uh, rate of heat transfer as compared to free convection. So that's why this statement 3 is incorrect. So that's why option A would be the correct option. Statement 1 and 2 are only correct, not 3. Does that make things clear?
Yes, sir.
So how was that example of keeping the fan off and on? You can physically feel the difference, right? Okay, so that ends questions from my side. If you have any questions from your side, it's time to fire them away. Do you have any questions?
Sir.
Okay, so with that, we will end our session.